Generator feeders running to a transfer switch are not considered a service entrance. To understand why, let's examine the definition of a service entrance according to electrical codes, primarily the National Electrical Code, or NEC. The service entrance is defined as the conductors and equipment that deliver electrical power from the serving utility to the premises wiring system. This typically includes the service drop or service lateral, the service entrance conductors, and the main disconnecting means. Key to this definition is the connection to the utility grid. The service entrance is the point where the utility's responsibility ends and the customer's responsibility begins. Now, let's consider a generator and a transfer switch. A generator is a source of electrical power, but it is not the serving utility. It's a standby or emergency power source that operates independently or in parallel with the utility. The transfer switch is a device used to switch the electrical load between the utility power and the generator power. When the utility power fails, the transfer switch disconnects the load from the utility and connects it to the generator. When the utility power is restored, the transfer switch reconnects the load to the utility and disconnects it from the generator. The feeders from the generator to the transfer switch are simply conductors that carry power from the generator to the transfer switch. They are part of the customer's premises wiring system, not part of the service entrance. They do not connect directly to the utility grid. Therefore, they cannot be considered a service entrance. Several factors differentiate generator feeders from service entrance conductors. Firstly, the source of power. Service entrance conductors receive power from the utility grid. Generator feeders receive power from a generator. Secondly, the point of connection. Service entrance conductors connect to the utility's service drop or service lateral. Generator feeders connect to the generator's output terminals. Thirdly, the purpose. Service entrance conductors provide the primary source of power to the premises. Generator feeders provide a backup or emergency source of power. Fourthly, the overcurrent protection. Service entrance conductors are protected by the main overcurrent protection device at the service entrance. Generator feeders are protected by overcurrent protection devices at the generator and possibly at the transfer switch. Fifthly, the grounding requirements. Service entrance conductors have specific grounding requirements to ensure electrical safety. Generator feeders also have grounding requirements, but they may differ from those of service entrance conductors. For example, a separately derived system, such as a generator, may require a grounding electrode conductor to be connected to a grounding electrode. The NEC provides specific requirements for the installation of service entrance conductors and generator feeders. These requirements are designed to ensure electrical safety and prevent damage to equipment. It's crucial to follow these requirements when installing or maintaining electrical systems. The NEC Article 230 covers service entrances, including the size and type of conductors, overcurrent protection, and grounding requirements. NEC Articles 700 and 701 cover emergency and standby power systems, including generators and transfer switches. Some specific considerations for generator feeders include, firstly, conductor sizing. The size of the generator feeders must be adequate to carry the maximum load that the generator is expected to supply. The NEC provides guidelines for determining the appropriate conductor size based on the generator's output rating and the expected load. Secondly, overcurrent protection. Generator feeders must be protected by overcurrent protection devices, such as circuit breakers or fuses. These devices must be sized to protect the conductors from overloads and short circuits. Thirdly, grounding. Generator feeders must be properly grounded to ensure electrical safety. The grounding requirements for generator feeders may differ from those for service entrance conductors, especially in separately derived systems. Fourthly, transfer switch. The transfer switch must be rated for the maximum load that the generator is expected to supply. It must also be designed to safely switch the load between the utility power and the generator power. Fifthly, labeling. All components of the generator system, including the generator, transfer switch, and feeders, must be properly labeled to indicate their function and voltage rating. It's also important to consider the coordination of overcurrent protection devices in the generator system. The overcurrent protection devices must be coordinated to ensure that the device closest to the fault opens first, minimizing the extent of the outage. For example, if a short circuit occurs on a generator feeder, the overcurrent protection device at the generator should open before the main overcurrent protection device at the service entrance. This prevents the entire premises from losing power. Let's delve deeper into the specific NEC articles that pertain to service entrances and generator systems. NEC Article 230, Service Entrance, provides comprehensive guidelines for service conductors and equipment. This article covers aspects such as service drops and laterals, service entrance conductors, disconnecting means, overcurrent protection, and grounding. It specifies the requirements for conductor size, ampacity, and protection against physical damage. It also outlines the rules for installing service equipment, such as service disconnects and overcurrent devices. NEC Article 700, Emergency Systems, addresses the installation and operation of emergency power systems, which are intended to supply power to critical loads when the normal power supply fails. This article covers generators, transfer switches, and other components of emergency power systems. It specifies the requirements for the capacity and reliability of emergency power sources, as well as the testing and maintenance of emergency systems. NEC Article 701, Legally Required Standby Systems, covers systems that are required by law or governmental authority to supply power to specific loads in the event of a power outage. These systems are similar to emergency systems but may have different requirements depending on the specific application. This article also covers generators, transfer switches, and other components of legally required standby systems. It specifies the requirements for the capacity and reliability of standby power sources, as well as the testing and maintenance of standby systems. Furthermore, NEC Article 702, Optional Standby Systems, addresses systems that are not legally required but are installed to provide power to non-critical loads during a power outage. These systems are typically used to improve the reliability of power supply to essential equipment or to provide convenience for occupants. This article also covers generators, transfer switches, and other components of optional standby systems. It specifies the requirements for the capacity and reliability of standby power sources, as well as the testing and maintenance of standby systems. Considering the grounding requirements for generator feeders, it's important to distinguish between grounded and ungrounded systems. In a grounded system, one of the conductors is intentionally connected to ground, providing a reference point for voltage measurements and helping to limit voltage surges. In an ungrounded system, none of the conductors are intentionally connected to ground. Each type of system has its advantages and disadvantages, and the choice depends on the specific application. For generator systems, the grounding requirements are typically specified in NEC Article 250, Grounding and Bonding. This article provides detailed guidelines for grounding electrodes, grounding electrode conductors, and bonding jumpers. It also covers the requirements for grounding separately derived systems, such as generators. In a separately derived system, the generator is not electrically connected to the utility grid, and it must have its own grounding electrode system. The grounding electrode system typically consists of a ground rod, a ground ring, or a connection to a metallic water pipe. The grounding electrode conductor connects the generator's neutral point to the grounding electrode. The size of the grounding electrode conductor is determined by the size of the generator's conductors. In addition to grounding, bonding is also important for electrical safety. Bonding is the process of connecting all metallic parts of the electrical system together to create a lower impedance path for fault current. This helps to ensure that overcurrent protection devices will operate quickly and effectively in the event of a fault. Bonding jumpers are used to connect metallic enclosures, raceways, and equipment to the grounding system. The size of the bonding jumpers is determined by the size of the conductors. It is also essential to understand the different types of transfer switches available. There are two main types of transfer switches: firstly, automatic transfer switches, and secondly, manual transfer switches. An automatic transfer switch, or ATS, automatically switches the load between the utility power and the generator power when a power outage occurs. The ATS continuously monitors the utility voltage, and when the voltage drops below a certain level, it automatically starts the generator and transfers the load to the generator. When the utility power is restored, the ATS automatically transfers the load back to the utility and shuts down the generator. A manual transfer switch, or MTS, requires manual operation to switch the load between the utility power and the generator power. The MTS typically consists of a switch or a set of switches that allow the user to select either the utility power or the generator power. When a power outage occurs, the user must manually start the generator and switch the load to the generator. When the utility power is restored, the user must manually switch the load back to the utility and shut down the generator. The choice between an ATS and an MTS depends on the specific application and the level of reliability required. An ATS provides a higher level of reliability and convenience, but it is more expensive than an MTS. An MTS is less expensive, but it requires manual operation and may not be suitable for critical loads. Finally, let's consider some common mistakes to avoid when installing generator feeders. Firstly, undersizing the conductors. It's crucial to size the conductors adequately to carry the maximum load that the generator is expected to supply. Undersized conductors can overheat and cause a fire. Secondly, improper overcurrent protection. It's crucial to protect the conductors with appropriately sized overcurrent protection devices. Overcurrent protection devices that are too large will not protect the conductors from overloads and short circuits. Thirdly, inadequate grounding. It's crucial to ground the generator system properly to ensure electrical safety. Improper grounding can create a shock hazard. Fourthly, neglecting coordination of overcurrent protection devices. It's crucial to coordinate the overcurrent protection devices to ensure that the device closest to the fault opens first. Failure to coordinate the overcurrent protection devices can result in a widespread outage. Fifthly, failing to label the components of the generator system. It's crucial to label all components of the generator system to indicate their function and voltage rating. Failure to label the components can create confusion and increase the risk of electrical accidents. By understanding the definition of a service entrance and the requirements for generator feeders, you can ensure that your electrical system is safe and compliant with the NEC.